Hello and welcome, everyone. Sorry for the technical issues. I'm glad to be here and to present my latest results, part of my PhD, with the topic Dioxygenase catalyzed hydroxylation of heterocyclic arenes. Let me start with the question. Why should we even work on heterocyclic arenes? Why are they interesting? Because nitrogen heterocycles are among the most significant structural components of pharmaceuticals and pesticides, like seen in these examples here. Over 60% of small molecule drugs contain at least one nitrogen heterocycle. One interesting and quite challenging reaction is the enantioselective and retroselective oxyfunctionalization of these compounds. For instance, for the generation of this tetrahydroquinone for all moiety shown on the left side here in blue, there are only 3 routes described in literature. 2 chemical ones performed starting from the ketone using heavy metal catalysts under more or less quite harsh reaction conditions, and 1 biochemical one using Pseudomonas wild-type strain. So when you think about biocatalytical hydroxylation reactions, the first enzyme that normally comes to our mind are the quite well-studied cytochrome P450 monooxygenases. Nevertheless, there is another enzyme family also capable to perform hydroxylation reaction. The weak and non-heme iron dioxygenases, in literature quite often referred as non-heme analogues of the cytochrome P450s, are capable of hydroxylating heteroaromatic compounds. Their natural reaction is the cis dihydroxylation of aromatics. They are a multi-component system consisting out of three parts: the reductase, the thyroxine, and the oxygenase. The reductase, which oxidizes NADH or NADPH, transfers the electrons to the thyroxine, which shuttles them then further to the oxygenase, which is incorporating molecular oxygen into an aromatic moiety, yielding this quite interesting cis dihydrodiene diols. One astonishing feature of these enzymes is that they perform quite a broad variety of different reactions, not only the cis dihydroxylation, but all the monohydroxylation, trihydroxylation, dealkylations, desaturation, and sulfoxidations. And that on a variety of different substrate or substrate groups, as you can see here. But what is so far known for the dioxygenase catalyzed hydroxylation of heteroaromatics? There are 2 major points. First one, that they are accepted as substrate, yes, but they yield only monohydroxylated products due to the instability of the heteroaromatic dihydrodiol, shown here. They eliminate spontaneously water and yield the re-aromatized alcohol. The second point is that aromatics are preferably hydroxylated over heteroaromatics within the same molecule. One question that we wanted to address is if the selectivity towards the hydroxylation of the heteroaromatic moiety could be achieved via enzyme engineering. That means from the aromatic one shown here to the heteroaromatic. So our first strategy was to screen 8 different wild-type dioxygenases for their ability to mono or dihydroxylate these 6 heteroaromatic compounds shown on the left side. In dark blue, you can see conversions over 50%, in light blue conversions below 50%, and in white, no detectable conversion. As you can see, the most promising 2 dioxygenases were the CDO and the TDO, the cumene dioxygenase from Pseudomonas fluorescensis and the taurine dioxygenase from Pseudomonas cutida, which were both capable of hydroxylating mono or dihydroxylate each of these 6 tested compounds. Due to the fact that the TDO shows promiscuous reactions towards over 150 different substrates, and that is one of the best studied dioxygenases, we decided to choose to work further with the TDO and to use it for enzyme engineering regarding the activity and selectivity for heteroaromatics. For the library design, we use the semi-rational approach based on the 3DM database of bioproduct. The 3DM database is a protein superfamily platform where amino acid sequences and hotspots are deposited. From over 8,000 dioxygenase sequences, which can be found there, we created a subset of 671 dioxygenases with, out of the subfamilies toluene dioxygenase, cumene dioxygenase, and naphthalene dioxygenase. Then we evaluated their amino acid occurrence on the two areas. The first one is the active site, shown here in purple, around the iron, the catalytic iron. And the second one, the substrate entrance channel, shown here blue, with the residues again in purple. Yeah, and in the end, we designed a library targeting 151 single point variants at 45 different positions, so combined in the active site and in the substrate channel. And this library was generated in collaboration with our cooperation partner Selecta from Leipzig. We tested this this library, the whole library, for a variety of different substrates, and I want to talk about especially 4 substrates here. For each of these substrates, we had different questions. So, for example, naphthalene, which we used as control substrate, we want to answer the question how sensitive the whole toluene dioxygenase is towards mutations in the active site. For the tetrahydroquinone, the number 2, we wanted to address the question if aromatic dihydroxylation on the aromatic ring here, or alpha allylic monohydroxylation in this position is occurring. For the tetrahydrobenzacetylene, number 3, we wanted to evaluate the influence of the ring size. So how is the ring, the substrate size influencing? So from a 6-membered ring, from number 2 to a 7-membered ring, is it still accepted as a substrate? And for the last one, the 2,5-pyridine, number 4, we had a question, can the radioselectivity be switched from the aromatic moiety to the heteroaromatic one? And as you can see, the substrate gets directly more demanding. Yeah. In the next slides, you will always see the variants that show the most astonishing results, I would say. So the highest activity or the best alteration in radio or enhancer selectivity. Here for naphthalene, only one product could be obtained, and the one from literature, and that is a quite nice thing why we also choose it as a model substrate, because only 1,2 hydroxylation can occur. The 2,3 hydroxylation is not possible due to the fact that 2 radicals would be formed. And you can see that 2 positions, the M220 and A223, are showed higher activities towards this substrate by remaining the same EE values, so the enantiomeric excess for the plus dihydronaphthalene diol with an over 99, except one variant or one position there, 366, showed little less activity than the wild type, but therefore nearly a complete switch from plus 99 from an enantiomeric excess from plus 99 to minus 90. So the other enantiomer was built up. We took this variant, made also a preparative biotransformation in a 100 milliliter scale, and could obtain 1 gram per liter in the end, so 100 milligram of this quite interesting product, which is also which so far could not be chemically synthesized and also not biocatalytically. For the next substrate, the tetrahydroquinone, which was never tested with the toluene dioxygenase before, 2 substrates popped up. The one pharmaceutically quite interesting, tetrahydroquinone 4-ol, here shown in blue, and the other one, the quinoline, the hydrogenation product. And in this graph, you always will see you can see the overall yield of both products together and below the selectivity. So in blue for the alcohol and in black for the quinoline. And again, you can see the positions M220 and A223 pop up, which are, in this case, A223, not only more active by 7 times for the interest in alcohol, but also more selective. That's quite interesting. And in addition, for the position M220, the selectivity could be switched into favor of the quinoline. And also, the position F366 this time had no influence on the enhancer selectivity, but therefore on the product outcome. So again, also here, the quinoline was favored. And for all the tested, or for these tested variants, the E value was above 98. the enantiomer success was over 98%. Yeah. For the next substrate, the tetrahydrobenzacetine, which was also never tested with dioxygenases before. The first thing is we have an activity, so 7-member rings are still accepted, and it is approximately in the wild type is approximately in the same range like for the 6-member ring. And here we could obtain two different products and two different monohydroxylated bonds, so in the alpha position and in the beta position. And as you can see, again, two positions pop up, the 220 and A223, which are both located in the active site of the TDO. And again, the A223T shows not only a higher product formation, but also higher selectivity to one of the products. And here, the M220 shows selectivity towards the other product. Yeah. And for our last substrate, the 2,5-pyridine, it was quite astonishing because the substrate was tried before in literature, and one product was described, the hydrodiendiol on the aromatic compound. But we could also already in the wild type see that there is a hydroxylation on the heteroaromatic compound. And with the variant M220C, we could even change it or push it a little bit into the direction of the heteroaromatic hydroxylation. And you see again, there are variants that are increasing the product formation by 6 to 7 times. Yeah. And to sum this up, it seems like the position M220 and A223 in the active site of the TDO are highly influencing not only the activity, but also the review and chemoselectivity. And that the active site position F366 is strongly influencing the enhancer selectivity, like shown on the example of naphthalene. In addition, we could synthesize this quite pharmaceutically interesting tetrahydroquinone 4O, which was produced not only in good yield, but with a very high enhancer selectivity. Furthermore, the heterocyclic moiety of 2,5-pyridine can be hydroxylated via TDO, which was so far not reported in literature. And yet, it seems like already single mutations in the TDO have a strong influence not only in activity but also in product distribution. And an outlook is at the moment we have ongoing the second library where we combine the most promising of these three positions, M220, A223, and F366, where we combine them and evaluate them regarding then the product distribution of the activity. And with that, I'm on the end of my talk and want to thank, of course, the organizers of this great event, Professor Hauer, for the opportunity to make my PhD at this institute, my master student Jonas Schelle, and Andreas Vogel, Michael Birkmann, and Gregor Hoffmann from Selecta. And of course, also a great thanks to the BMBF, from which we received funding in the course of the project Power Card. Thank you very much for your attention, and I would be glad to answer some questions.
Okay, thanks very much, Julian, for a fantastic talk and fantastic results. Anya, can I hand over to you to mediate the Q&A session?
Sure, yes, thank you. Thank you so much, Julian, for an excellent talk. So we have a question from Marco Freie. I was trying to unmute Marco, but I don't think I have the right to do so. So maybe I can read the question. So the TDO enzyme was once studied with the aim to produce indigo from indole. Were your mutants tested for this, and did you observe indigo when growing cells?
That's a very good question, and indeed, yeah, because indole is a degradation product of tryptophan, so you have always a little bit of it in your cells. And indeed, when you express the TDO cells, you get always a blue color, so we have always indigo formation. But it's quite easy to get rid of it when you use a mutant strain where the tryptophanase is knocked out. Then indole formation is inhibited, and also the indigo formation is not occurring anymore. So with the TNAA, I think the tryptophanase, the hydrogenase, tryptophanase, yeah. And then you knock it out to get rid of this problem, because indeed indigo is a quite nasty compound to get rid of if you want to purify your products.
Perfect. And I have another question from Roberto Chica. So thanks, Julian. It was a really nice talk. Do you do anything special to solubilize your substrates? What concentrations are you using?
Substrate concentration are always 10 millimolar, and we isolubilize it in ethanol. That is perfectly, because if you use DMSO, it is also possible. But again, DMSO, if you make it in a larger scale or semi-preparative scale, is nastier to get rid of. So 10 millimolar end concentration, but for naphthalene, for example, also 20 or even 30 millimolar can be converted to 100% even. Yeah.
Perfect. I propose if people have other questions, maybe they should continue typing them into Q&A window, and our speakers will answer them in that window. And I'll hand it over back to Anthony.
Okay, thank you very much.